All right, good day, class. So this is lecture 5, the equilibrium of a rigid body, and still under the statics of rigid bodies. So before, if we were dealing with equilibrium of a particle, then the force systems under particular particles, or in this case, force system resultants. For this particular topic, we're now going to be identifying the reactions and supports. So just to recall, you've been doing these particular problems before, trying to determine the moment of the force, trying to determine the force involved here in previous lectures, like lectures 2 and 3, um, whether they're be in 3D or 2D, in Cartesian vector form or in scalar form. And notice that the only thing missing here is we're not exactly looking for the reaction on the supports. So we haven't accounted for the reaction that this particular supports generates, or in this particular, this fixed support, this roller, this spin support, fixed support again. Um, you can call this fixed support, fasten, basically. Okay. So for this particular lecture, we're gonna go over them. What are the conditions for rigid body equilibrium? What are the equations of equilibrium for a rigid body, which you would guess by now it's almost equal to the one we discussed before in equation in lectures 3. And of course, what are the types of supports and equivalent reactions? How to draw the free body diagram in 2D and 3D. Then, of course, sample problems to apply concepts learned. And yeah, okay. So for conditions for a rigid body equilibrium, as shown, this body is subjected to an external force and coupled movement system that is the result of the effects of the gravitational, electrical, magnetic, or contact forces. So whatever this body, rigid body system represents. Yung simplified force, basically, pag sama-samahin lang naman natin yun, all forces din into its resultant force. So basically, all force components will yield to zero kasi it should be rigid. Eh. It's not supposed to be unstable. Eh. Okay, and then of course the resultant moment, since the system is preventing movement, there should be no moment. Eh. Although there is moment, there is a counter or reaction that prevents that moment or the tendency to rotate. Eh. So we're gonna combine everything into that to become the resultant moment. Eh. Okay, some examples we have here is this. So this is a sample of what I call tensegrity. You can actually watch them. It could be for display or just actual practical artwork as well. Okay. So the internal force caused by the interactions between particles within the body are not shown in this figure, but because these forces occur in equal but opposite collinear pairs, hence everything will eventually cancel out, resulting with force resultant equals to zero, moment resultant equals to zero. Here are the types of supports and their equivalent reactions. So before, we're not considering, okay, what was the reaction of those supports? Because technically, we are neglecting their weight before. But this time, although on some occasions we will still neglect the weight, but this time we are now considering the reaction on the supports. So what are support reactions? So, okay, support reactions, a support prevents the translation of a body in a given direction by exerting a force on the body in the opposite direction. Okay, so if there's a force applied here, the reaction there's an equivalent and opposite reaction here in the fixed support. So for example, there's a downward force here. The reaction against that, there will be a reaction in the fixed support here at Fy. Okay, a support prevents the rotation of a body in a given direction by exerting a coupled moment on the body in the opposite direction naman. Okay? So if there's a moment here, there's an opposite moment the other way around. Here, sometimes if your supports, you've seen this problem or you've seen this drawn. These are type of roller supports. This is a roller supports. They just look differently, but they still look the same. This means that horizontal movement is allowed, but it's not the movement it's trying to prevent is it go down further. There's also the fixed support, and normally they're welded, sometimes fastened by a flange, so with a bolted nut, then a flange. So here are your types of supports for rigid bodies subjected for two-dimensional force systems. We have here a cable, so we have here a force or a tension. This is one unknown, and um, the thing is nangyayari dito is kasi may pulling action dito. So yung reaction niya is tension force going down. The reaction is a tension force which acts away from the member in the direction of the cable. Then here is a weightless link. So again, it's the same thing. Action neto is if it's a weightless link, so it's not exactly a cable keto. So if it's being pulled, meaning there's a reaction of tension here. It's being pushed, there's a reaction of to compress it here. So one unknown, the reaction is force which acts along the axis of the link. It's a fix. Then of course we have the roller as shown below, and it's normally perpendicular to the force. Okay, the reaction force is which acts perpendicular to the surface at the point of contact. These are pretty important reactions, so that when you draw your free body diagram, you know where the forces are and what kind of forces they are. Okay, and what the orientations are. So pag sinabing roller, okay, it's supposed to be a perpendicular distance dun sa reaction on those support. Here are the others. Here's a rocker, which is pretty much the same thing as the roller. The action is also which acts on a perpendicular to the surface. The same way also with smooth contacting surface. So basically 3, 4, 5 pretty much is the same thing lang naman. Also here roller or pin, one unknown. The reaction is a force which acts perpendicular to the slot. Then we have here a member pin basically connected to a collar or the smooth rod. So one unknown, the reaction is a force which acts perpendicular to the rod. So this one allows horizontal movement or depending what kind of movement it does, but prevents up and down movement. Here naman we have a smooth pin or hinge which madalas natin makikita sa problem natin, which uh, causes two unknowns. So the reactions are two components of force or the magnitude and the direction theta and the direction phi of the resultant force. Note that phi and theta are not necessarily equal, usually not, unless the rod shown is linked in, as in number 2. So for bakit yung reaction niya horizontal and vertical forces dito? Because the one thing that it doesn't prevent is this moving side by side, but what it prevents is nakapin siya, smooth pin or hinge, it prevents upward and downward movement. Upward, so vertical movement and horizontal movement, except rotation lang. Okay? Remember, fixed connected to a collar on smooth rod, this one, two unknowns. The reactions are the couple moment and the force which acts perpendicular to the rod. So what it prevents is its moving force and a moment, but it doesn't prevent it from moving upwards or downward. Okay. Here naman is basic fixed support. Basically, a reaction nito, aside from its weight, it also prevents the moment. So there's a reaction on the Y force, reaction on the X, the horizontal force, and reaction on the moment. Notice that the default representation of the forces here are on its positive. So we're gonna go back with going right for the horizontal force Fx as positive, going up Fy as our positive, and then counterclockwise of moment as our positive. Our equations, our equations of equilibrium, once we solve them, if it yields a different sign, meaning our representation of our free body diagram was wrong, or our initial assumption was wrong. But we will get to that later. Now, for the free body diagram, it's better to solve some sample problems and to show you how it's done. So we have here a sample figure. We are here to draw the free body diagram of a uniform beam shown in figure shown below. The beam has a mass of 100 kilograms. It's not exactly shown here, but there's an applied force of 1,200 newtons, 2 meters from point A. And the total length of the beam is 6 meters. There are some rules to consider. So you have to draw your axis first. So when you're drawing your FBD, you draw your axis. In this case, I base my origin at point A. There we go. Now we draw a representation of a body. So this time, since we're talking about equilibrium of a rigid body, we gotta draw at least a representation of the body. In this case, a line. Next is we reflect now the forces. So first things first is, since this is a uniform beam, so that's 100 kilograms there. So it's supposed to be applied in the middle. So that's 3 meters away from point A. So that's 100 kilograms times 9.806. That's 980.6 newtons or 981 newtons. Then of course that's 1,200 newtons applied 2 meters away from point A. And of course the reaction in the supports here, AX and AY. In this particular case, it was already assumed to be on the negative side, opposite. But by default, I would place it just like so. I would place it here first before assuming it on the left side already. So I will place AX here first. Then I will let my equation equilibrium to dictate if I am correct or not. So that's how you draw it. And then finally you reflect the dimensions. Then obviously the next step here is to solve the required, which is usually the force reactions here, so to determine the AY and AX. And you do that by establishing force equilibrium and the moment equilibrium. Let me just remove this. Okay, so let's try to actually solve a problem. So determine the horizontal and vertical components of reaction at the supports. Let's neglect muna yung thickness of the beam. So we have here a pin and a roller. So there you go. So first things first is to identify muna what are the supports being provided. So we have here a pin, normally projected by this, and a roller. A pin is a fix. Support. The roller, uh, that's just it. Nakapatong lang sa kanya yung beam. Dito, it prevents yung upward. Hindi mo siya mahihila and hindi mo rin siya mausog horizontally. Okay, this one pwede, but ang reaction lang naman niya putangin dito is just going up perpendicular force. This one, you know very well na dalawa kagad yung reaction niya. Isang vertical, which is AY, and then isang horizontal, which is AX. And we have following dimensions. And please do not forget, we also given a 600-pound force feet moment, and this is clockwise, so we know that this is negative. We also have a applied force of 500-pound force at an angle, which is 5 feet, so we can get its x and y component in. So we're asked to find the reaction that supports A and B. Our solution muna is, of course, to draw the FPD. So we draw first the axis, then we draw a body, a presentation of the body. So this point A and point B. In this case, again, nirefer ko lang yung point A as yung origin ko dito. Okay? Doesn't matter, really. And then we put yung reaction on supports. So for A, we have AY and then AX. So here's the given muna, 500, 3 over 5, that's your horizontal force. And then you have 504 over 5, that's your vertical force. And then you have your moment, 600-pound force feet. Then the additional AY, BY, and then AX. So perpendicular to the roller naman, to the object to. So that's BY. We have a reactional support dito, which is AY and AX, kasi that's a pin. Okay, there's two unknowns. You have two unknown reactions dito, AX and AY. So we assume them on the positive end pa dito. So upward as positive, rightward that's positive for the horizontal force. Then of course, finally, we add the own dimensions. Okay, just a note, we assume our components to be in the positive direction, and then we correct them should our equation of equilibrium says otherwise. So the next step, of course, is establishing equation of equilibrium, and just shortcut it and solve them simultaneously. But that could be your number 3. Okay, so first things first, we sum summation of all x forces on the horizontal axis equals to 0. So ano yung mga x forces natin? So we have ax plus 500, 3 over 5, And that's pretty much it, equals to 0. And from here, makukuha natin na AX is equals to negative 500t over 5, which is equals to negative 300 pound force. But let's double check. It says here negative, but our sign here is positive. Our orientation here is positive. This only means that from our FPD, our assumed direction is wrong. So we will update our free body diagram later. Okay? So let's solve naman for summation of forces in the vertical naman. So FFY equals to 0. So what do we have? AY minus 500 over 4 over 5 plus BY equals to 0. So from here, we have two unknowns, and technically we cannot solve it. So we need another equation. Not this one because we already used this. So this time we establish yung equation of equilibrium for moment. So we're gonna take a moment. You can choose, pero ako pinili ko use yung moment about A so that it cancels out yung AX and AY, leaving BY na lang. So it's really up to you. So you can also choose yung BY as your point of moment, but you would have to use yung AX mo naman dito. So for me, for simplicity, try to eliminate two forces at the same time lang muna so that leaving me with one unknown. So I'm gonna take a moment about point A, which would yield this particular equation. So paano yun? Negative 4, it's gonna be negative 500 4 over 5 since it's gonna be clockwise about point A times 5 feet. So 5 feet yung perpendicular distance. So we have BY naman dito, which is counterclockwise about point A. So that's 10 feet. So BY times 10, that's pound force feet. Then AY here is simply cancel out since there's no moment, there's no perpendicular force. And then we already have a given 600 pound force feet. So we include that to our equation. So it's gonna be about point A clockwise. So that's negative 600 pound force feet. And then from here, we can now solve BY. And isolating BY, transposing and rearranging the equation. Then don't forget to cancel units. Don't forget to do unit analysis. So this case, 504 over 5. I know na all of them are pound force feet. So nilagay ko na nasa dulo. And then just cancel out the 10 feet divided by 10 feet. BY now, the force BY is 260 pound force. So far, so good. And then from here, we can now solve it. So technically, this is our equation 3, so to speak. This is our equation 2 and equation 1. 3 equations, 3 unknowns, so not bad. Now we solve for AY, we just simply just substitute BY here, and we will get 140 pound force. Okay, since our AX, our horizontal force at point A, is negative 300 pound force, our orientation is wrong. So we have to update our FBD. So in this case, an updated FBD is required. And we just have to redraw everything and then just correct the orientation of just one particular arrow, this one. If you got it right from the first time, then that's good for you. Pero for me, I always assume the positive yun. Then I'll just correct. It's a lot easier to correct na lang yung drawing than the entire equation. Okay? So for me, I assume everything muna is every orientation is going to be positive muna, and then I'll just correct myself na lang after seeing my equations of equilibrium and solving the equations simultaneously. Let's try another one. So here we are to determine the horizontal and vertical components of reaction at pin A, and at beam C. Okay, so pin A at beam C. So how do we do this? We're given 4 kilonewtons at point B, and we're here to determine the dimension, the reactions, the vertical and horizontal component reactions at the at beam at C and then at pin A. Okay, so essentially for A, since this is a pin, so we have two unknowns dito. For C, we have also two unknowns dito. So we have AX and AY. And then C, we have CX and CY. Of course, ang first step natin dito is to draw the free body diagram. So again, we draw a partial, we draw this one, a partial representation of their body. Okay, so just say may bar dyan, ano, okay, and then you cable dito. And then now we reflect the forces. Point A, so we get positive AX, AY. We assume muna na positive, then CX, CY. We have force C dito at an angle, but we will get that naman later. And then of course, applied yung given natin na 4 kilonewton at point B. Here are the given dimensions. Then of course here, you can also get the angle here by simply getting 1.5 and the tangent inverse of 1.5 and 1.5. So that's 45 degrees. And if you would notice, we didn't include supports on D since if you get the support of D is a totally different system. And if you would draw the free body diagram, it would look something like this. FD and then FC, where FD is equals to FC. So no need. So next is to establish the equation equilibrium, where summation of fx equals to 0. Huh. So that's gonna be ax plus cx, which is c cosine 45 degrees, by the way, equals to 0. That's our equation 1. For f of y equals to 0, ay plus cy, so that's c sine 45, minus 4 kilonewtons equals to 0. That's our equation 2. So how many na? So we have two equations and we have how many unknowns? 1, 2, 3, 4. So technically we need 4 equations. And then a summation of moment about A. So I just chose A because it's a lot simpler and it will cancel out AX and AY kagad. So AY is 0. So what else do we have? CY times perpendicular distance of 1.5 counterclockwise. So that's going to be positive. So that's C sine 45 times 1.5 kilonewton meter. Then we have 4 dito. 4 times perpendicular distance of 1.5 plus 1.5. So that's 3. So it's going to be 4 times 3 clockwise. That's negative 4 times 3 kilonewton meters. That will be our equation 3. And from here, we don't exactly need another equation. So really depends. I think we can pretty much solve everything from here. Say with the first equation, that's completely solved. Equations 2 and 3 are meant to solve AY and C sine 45. So the additional 2 equations is needed. So no need for additional one. So now we solve for the unknown. We start with equation 3. So we're now able to solve C here and isolate it. And we get the product of 4 and 3 divided by the product of sine 45 and 1.5. For C now is simply 11.3134 kilonewtons. That's for C. Cx is just by trigonometry. So the x force is just simply cosine, in this case, what? Sine, yeah. No, it's cosine pala. It's cosine 45 degrees, and then Cy is just simply C sine 45 degrees, which is 8 kilonewtons. Okay, if you get the sum of the squares and square root of it, you will get 11.31 kilonewtons. Next up is for AY. So we simply substitute the C sine 45 and you will get this negative 4 kilonewtons, and then we simply substitute those equations there. We will get AX as well as negative 8 kilonewtons. Okay. However, again, checking it. Let's check again. Negative 4 kilonewtons and AX is negative 8 kilonewtons. Checking on our FBD, our orientation of our arrows is actually wrong. However, initial FBD is wrong. So we have to update the FBD. So here's the updated version. All we have to do is just draw them. Since positive yung CX and CY natin, we are on the proper orientation here. So that's good. So ang mali lang is AX and AY. So all we have to do is just redraw AX and AY and then on its proper orientation, just like so. So that is for 2D. Now we go for equilibrium of rigid body for 3D naman. So again, it's the same concept. And then for all the force resultant and its components are going to be equals to 0, except we could just going to combine them with the x and y and z axis. I hat, j hat plus k hat. Okay, just don't forget the resultant force, the square root of all x, the square root and the sums of x, y, z components nila, and then get the square root nila. So the squares are the sums of x, y, z axis, and then square root, that will be your force resultant. The same way with your moment resultant, and its components are gonna equal to 0. So if may supportive rigid bodies rin, meron rin tayong, for two-dimensional, meron rin tayong supportive rigid bodies subjected to three-dimensional forces, and you can find this at page 256 on your book. Okay? So in this case, cable, the only difference na naman, it's being shown in 3 dimensions. Okay? In this case, cable, so there's tension lang dito, and there's just one unknown. And the force it's trying to prevent, yun yung reaction force niya. No? Okay, we have a smooth surface dito, rollers, so just perpendicular force lang yung reaction niya to the surface at the point of contact. That's both of them. And then of course we have yung roller, okay? And then we have a ball and socket. Notice yung reaction. The ball and socket joints, kung ang pin so for ball and socket joints, yung equivalent version nito would be yung pin. While pin allows for some certain degree of rotation, here the ball and socket joint allows for the arm to move at not just in one dimension but also in 3 dimensions. And the one thing that it prevents is upward movement sa z-axis, horizontal movement sa x-axis, and of course yung y-axis rin. So those are the kinds of reaction, those are the forces that it's trying to prevent rin, yung ball and socket joint. Okay? Next one is single journal bearing, which is really popular for machines, especially with long shaft. Okay, so that there's not much moments there. So there are 4 unknowns dito. The reactions are 2 forces and 2 coupled moments, and which are perpendicular to the shaft. Okay, so bakit? Kasi if you would notice, the ball, this one allows for some y, in this particular orientation, it allows for y-axis movement and allows for moment about the y-axis rin. But it prevents moment about the x-axis, which prevents also x-axis movement, and prevents moment about the z-axis, which prevents na mahatak mo rin siya. See? Now there's another type of single journal bearing. This one is quite specific, with square shaft naman siya. So this time, pine-prevent naman niya yung paggalaw niya along the y, z, and x-axis. Ganon rin yung moments niya along the y, z, and x-axis. Okay? Normally, hindi ko pa siya nakikita ng ganito. Pero so, pag nagmamachine shop kayo, most likely nandun yun. Then of course, there's yung single thrust bearing. 5 unknowns, the reaction are 3 force and 2 coupled moments. The coupled moments are generally applied. So pag sinabing single thrust bearing, one force usually one portion ng design na to is pinipigilan yung movement. In this case, it's trying to prevent an Y movement. Okay, so it's only one direction lang dapat ang allowed na movement niya. Okay? So meaning fixed support yung FY dito. Then of course yung single smooth pin. Okay, just like the only difference here is allowed siya mag-rotate in this particular orientation, allowed siya mag-rotate along the x-axis, hence there's no moment reaction dito. But it's trying to prevent moments along the y and z axis, and it's trying to prevent na mahatak siya along the z and y axis as well. Okay? And of course, you're trying to prevent it to move along the x-axis length, but moment along the x-axis is allowed. Now, sorry. Here naman we have a single hinge. Normally makikita nyo sa mga pintuan natin, sa mga toolbox. If you notice yung natural reaction niya, you're allowing movement on one particular axis. So there's movement there, but you're trying to prevent it mag-rotate along this particular case, the x-axis and the z-axis. Kaya nga may hinge. And since naka-hinge yan, you're trying to make sure that that body is rigid enough so that hindi mo siya mahihila along the z, the y, and x-axis. Okay? Hence, yun yung equivalent reactions niya. So, yung mga reactions dito, those are the forces that you're trying to prevent so that yun yung those are the forces that it's trying to prevent so that it keeps the body at equilibrium. Okay? Sure. Correct. Yeah, tama naman. Then, of course, we have yung fixed support. And the fixed support could be a fixed support, a pipe fixed support about a flange, uh, and then fully secured by nuts and bolts and flange, and a welded flange, but then on the welded structure, something like that. So in this case, it's 6 unknowns. So this one, you're trying to prevent rotation about the XYZ axis and movement along this X, Y, and Z axis as well. Okay. You normally see fixed support, smooth pins, uh, ball and sock. No, so single journal bearing and piping configurations. You would see rollers lagi on piping. Hence, these are the samples that I chose for this particular topic. And there are a lot of impractical designs done, which just a matter of mental exercise really for equilibrium of rigid body. But I chose more those are that are practical, the one you would see normally in a plan. So notice if you would see in a construction industry, you would see piping hanging around. So may mga cables doon, may mga supports, may mga links, may mga U-bolts. And then of course, pag nasa baba naman, pag may mga pumps, meron kang support structure. Sorry. And then, usually in between ng cement and ng pipe is a roller that would act as support. So, let's try to apply some practice, some warm-up sessions muna na sample problems so that we know how to do yung free body diagram, at least for 3D. It's just a matter of orientation lang naman lang rin. So here, we just gotta ignore muna the weights of the options shown below. Let's try to determine where the reactions are, the supports, via drawing the free body diagram. So we have a properly aligned journal bearing at point A, B, and C. So here we have a pin at A and cable BC. So we have a cable dito. And here we have a properly aligned journal bearing at point A, hinge at point C, so parang siyang door hinge, and then a roller at point B. Then an applied force at 400 pounds somewhere in between here. Okay? Normally may given dimensions yan, pero in this case, we can say it's arbitrary lang muna. Okay, let's start with this. You may pause the video muna so you can try to determine your own. So you're applying the same principles as if you're drawing free body diagrams in 2D, but you just have to draw it in 3D lang. So the same rules apply. Except there's a z-axis now. So x, y, and then z-axis. So you may pause this video and you may try this yourself muna. Okay, let's give it a go for the first one. So the first things first you want to do is you may want to draw your XYZ axis muna. And then, just like we did before, we draw your partial body nito. And now, we draw the reactions on the supports naman na. So in this case, this is a aligned journal bearing. So this one is trying to prevent AZ and AX, basically. AZ and AY pala. So we assume them on the positive directions again. So AZ going up, AY going the positive axis, and then we reflect yung 45 Newton meter. So we have another journal bearing heat here at B. So if this one is preventing BX and BZ. So BX and BZ. And just so you know, there's moment. If there's AY, AZ here, it's trying to prevent also yung moment across AZ and AY, BZ and BX. So for CX naman, this one is trying to prevent Cx and Cy. So the Cx positive and Cy. Then also there's moment in this trying to prevent moments in Cx and then Cy. Okay. This time, okay lang na hindi mo i-reflect yung moments. Okay lang makita ko yung supports. But you should know that there's gonna be a moment reaction here eventually. So let's try this one naman. So we have here 300-pound force hanging dito. And then 200-pound force feet rotating counterclockwise. And then we have a cable dito. Then pin at A, cable at BC. So again, we draw our XYZ axis. Then we draw our pin. So there we go, just for reference. And then we draw our, so we draw this particular body here, and then we draw our reactions. So for BC, it's just tension BC, basically. Since this is pin, so it's trying to prevent AX, AY, and then AZ. Okay. Yep, so that's pretty much it. And it's also trying to prevent moments in AZ and then in AX, but it's allowing movement across AY axis, across the Y axis pala. As you can see, 200-pound force feet. I just transferred it here. I think pwede naman yan. Then for here naman, for properly aligned journal bearing at A and hinge at C, and then roller at B. So it's gonna be something like this. You draw first the XY, you draw the body, now you draw the reactions. So for journal bearing, okay, you're trying to prevent it just like here, two forces of unknown and then two couple moments. So you're trying to prevent AZ and then AX. For roller, it's just perpendicular force upward, so that's BZ. Then for hinge, so you're trying to prevent CZ going up horizontally and then vertically, so CX and CY. Then you have your applied force of 400-pound force here with an X amount and Y direction dito. Okay? So this is how I expect you would, you can also, if you know where the moments are, that's good. But in this particular case, there will be no moments since there's already three supports are preventing any movement at all across the Z axis. There we go. Let's try for some actual sample problems. So here we have a uniform plate and has a weight of 500-pound force. Determine the tension in each of the supporting cables. So we're here to determine FA, FC, and FB. Or you could also label it as TA, TC, TB. It's fine. We have the following dimensions, and there's an applied force of 200-pound force. That's 2 feet from the y-axis and 3 feet from the positive x-axis. Okay, that's good. So first things first, we draw our free body diagram. So again, we draw first our x and y axis. Then we draw our body. Okay, since it says here, we're also given with another given here, 500-pound force. The uniform plate has a weight of 500-pound force. So it says here uniform plate, so that weight must be applied on the dead center of this plate. Hence, we draw this one. So again, you have a clue ready here. If it says the uniform plate, it's given the weight here, meaning the weight is applied in the middle. And then you apply the given first. So we have 200-pound force here and the 500-pound force here in the middle. So 1.5 from the x-axis and 2 feet away from the y-axis. Okay? The next here is the reactions. So we have cables here. So there's only tensions going upward. So tension A, tension C, tension B. So force A, force C, force B. And I think that's pretty much complete for our free body diagram, because the next step is the establishment of equation of equilibrium. So again, we do it step by step. So notice the summation of x forces is equals to 0 because there's technically no x forces dito. So it's literally no x forces here. Okay, there's also no y forces because there's no y forces here. So only z forces. So it's the combination of the sums of FA, FC, FB minus 200 minus 500. That will be our equation 1 because we have 3 unknowns. So technically, we need 2 more equations to fulfill the 3 unknowns, 3 equations paradigm. Okay? 3 unknowns, we need a few more equations here. Basically, we get 2 more. We get 3 unknowns, we need 3 equations. So we already have 1, we need 2 more. Next up is let's take a moment about the x. We can take a moment technically about the x and y axis. Technically, we can take the moments about the x and y axis to establish our 2 new equations, or we can be smart about it and or we can take the moment about x prime and y prime axis. Why do we why? So that we can eliminate a lot of forces at once and leave just one unknown, and you can solve them one at a time. Okay, if you would read your book, it doesn't say that you have to take the moment about its established x and y axis. You can rotate it about a particular axis just like so, x prime and y prime, so that it's easier to eliminate the forces and you can solve the equations scalarly. Oh yeah, going back there, since we're in 3D, it's not necessarily to solve this equilibrium of rigid body in vector form. But most of the time, even though it's still 3D, the good news is you can still solve them in scalar form, or primarily scalar. We will only be dealing with vector form if A, we're given a Cartesian vector notation, or we're dealing with cables and forces that are not along the x and y axis. But more on that later. This is more of a high level now. Okay, so if we do x and y prime axis, so the summation of moment across x prime, so you eliminate 200 FA and FC, leaving only 500 pound force counterclockwise, so that's 1.5 pound force feet, minus clockwise force B times 3 equals to 0. That'll be your equation 2. See, that's a lot faster then. And then from here, rotation naman about the y prime axis, about here. So you eliminate how many forces? 2. You eliminate FB, you eliminate FC, leaving you with 500, 200, and FA. So you will now have a moment FA times 4, 2 plus 2, 4. That's counterclockwise, minus 200 clockwise, pound force times 2 feet, minus 500 times 2 feet, since clockwise rin siya. And that will be your equation 3. And there will be no moment at z since technically there's no forces there and there's no perpendicular, there's no perpendicular forces. The next step is to solve the unknowns. We go first with 2 and 3. Here we will now be able to solve FB and FA accordingly. And FB would be 250 pound force since it's positive, meaning our orientation is correct. FA is now going to be 350 pound force, again positive since our orientation, that means our orientation in our FPD is correct. And then finally, we just plug it in on our equation 1 to solve for FC. FC is now equal to 100 pound force, again positive because our orientation here is good. So no need to redo our FVD. Okay. Again, you can rewind this video and then try solving it on your own. Try practicing on drawing faster in terms of your free body diagram so that you can establish your equation equilibrium much faster as well. But then again, with this type of problem, going slow is sometimes going fast. The more you're careful with your free body diagram, the more you're sure of what your equations of equilibrium are. Okay, let's try another one. Here, determine the reactions at the roller supports at A, the ball and socket joint at B, and the tension in the cable BC. Okay, so I like the problems because they're really describing what type of supports are at particular points, and we're given this much dimensions really. So we have a cable detail. Okay, so what do we do first? Of course, All we have to do first is draw our free body diagram muna. So we draw our x and y axis muna. X, Y, Z axis. We draw our body, and then we draw the given. First draw the given, and then the reactions to support. We have 900 newtons here and 600 newtons. That's in their particular dimensions away from the axis. Okay, I'm not gonna write it down here because it's gonna be messy. Um, and then let's put the reaction. So A is a roller. Roller suppose so there's only a y perpendicular to the point of contact. And then we have a ball and socket joint which prevents a x-axis, y-axis, and z movements. It's ball and socket joint. So that's that. Although it looks redundant, okay lang yan. And then of course we have tension here. Just call it FB or FBC. So pointing upward. So that's pretty much it. Next step here is to establish equation equilibrium, and here we got a summations about the horizontal for around the x-axis muna, which is 0. Technically, dx lang naman yun, so dx is equals to 0. Automatically, there's no dx. There's no reaction there. But it makes sense, given the type of support that it's providing, the body will not move at all. So 0 yung forces dyan. No reaction at all. And then at the y-axis, summation of forces along the y-axis equals to 0. And the only y-axis forces in the y-axis is dy. So that's dy equals to 0. Okay. So next up is, of course, the z-axis. So with z-axis, there's a lot of forces. We have az, we have dz, we have fb, 900 and 600. So it's going to be that az plus fb plus dz minus 900 minus 600 equals to 0. That will be our equation 1. The next one is the establishment of our moments equilibrium. So in this particular case, let's try to take a moment about the x-axis so that we eliminate az and fb, leaving only 900, 600, and dz. There we go. Then we eliminate az and fb, and we have here negative 900 rotating clockwise. We have 0.1 minus 600 times 0.5 on the x-axis, and then dz going upward, that's counterclockwise, that's 0.8. That's our equation 2. Then we have rotation about my. My naman is basically we eliminated fb and dz and only leaving az. So there we go. So that's gonna be az. That's gonna be clockwise. So negative az times 0.4 plus 0.4 plus 0.2 times 1, and then 900 counterclockwise. 0.4 plus 0.2, that's 0.6, and then 600, that's about positive rent times 0.2. That's our equation 3. So we can also go with the summation of moment about the z-axis, but that will only leave us with dx, which apparently is just 0. But it makes sense because given the support, it won't rotate that much na. It won't give that much. It won't generate that much moment force because the force reaction in dx is 0. So leaving the moment at z at 0. So there's no moment at all. So from here, we just solve the equations since we have enough equations already to solve our total number of unknown. So that's going to be az, fb, and dz. So from equation 2, we can now solve dz. So isolating dz, 900 times 0.1 Newton meter plus 600.5 times 0.5 Newton meter divided by 0.8 will give you 487.5 newtons positive. So meaning our orientation here is correct. For equation 3, we can now determine az, and if you arrange the equation, you will yield with this particular equation. So that's 900 times 0.6 plus 600 times 0.2 Newton meter divided by 1 will give you 660 newtons. Now that you know dz and az, you're now able to solve force B or tension at BC. That's going to be 900 plus 600 minus az minus dz equals to 352.5 newtons. And again, it's positive because our orientation is correct. Again, feel free. So that's the general gist of the equilibrium of rigid body for both 2D and 3D. Now, on our next meeting, I will be adding another sample, but this time I'm going to be using not scalar way of solving it, but more on vector analysis. But just to prove to you that you can actually solve them, um, you can solve 3D problems, equilibrium of rigid body, scalarly. So that's pretty much good news for you guys. Again, if you have any more questions, feel free to email me and contact me directly on Google Chats. Thank you.